start it up now, and since it was kind of a break in topics. See, we can actually use the same chi-square test for testing contingency tables. In other words, what if there are two different categorical variables and we want to test the difference between two different categorical variables? So in this case, we have two totally different categories. I'm going to test the interaction. Like we could have income groups. So if we ask everybody, what's your income, and we categorize those as high, medium, and low, and we ask, their gender, male or female, we could make a contingency table where we have male and female on one side, high, medium, and low, and then we could just put all the counts. And we could test whether or not those distributions was random, or whether or not it was there was some relationship between those categories. Okay. So in the last section, we looked at this, observed. In the new test, it's going to be the same way. This is a repeat of the slide, so won't spend too much time there. This is kind of like it's a categorical test for association. Later, we're going to discuss, and many of you probably have actually already done, like regression, looking at two variables that are numeric and seeing how well they're related. This is a categorical test for association. In other words, so we're covering the categorical first, and we're covering the numeric closer to the end. Okay? So if I wanted to test gender versus income levels and see if there was a difference, or race versus distance from X, distance from certain services or whatever, or actually distance would be. I can do anything I can do with the regression. I just have to break it up into categories. So in other words, distance has to be, a small distance, medium, large distance. Okay, race is a category already. Male and female is a category already. So both of your variables that you're testing here have to be divided up into categories to use this test. Okay, we'll talk later about the regression, but for this test, statistics find a chi-square test, it easily extends to two categorical variables. Because all we need to do is come up with a hypothesis and then expected counts. And those expected counts can be in a two having two categories. So everything's the same. The degrees of freedom is calculated a little bit different. So we'll talk about how that happens here in a second. Okay. All right. So here's our simple example this time. Here we've got a word preference. So whether or not you would think of yourself and your goal to earn an Academy Award, a Nobel Award, or an Olympic Award. In other words, is your like ideal to someday get an Academy Award, like for acting, Nobel meaning for your brains, I guess, or I think in this case they meant a Nobel Award for some academic field, not Peace Prize. And then the Olympic, or would you rather get an Olympic gold medal? Okay. And then we wanted to see if there's an interaction between this variable and a relationship between what you see yourself striving for and whether you got a higher score on your math or a higher score on your verbal. Okay? So do you think there's a relationship between a word preference and which SAT is higher? Okay? So this is the raw numbers. So these are the people that scored higher on math. These are the people that scored higher on verbal. These are the people that preferred to think of themselves as Academy Award winners, Nobel winners, and Olympic winners. Okay. This is what's called a contingency table. So the expected counts can be calculated as the row total times the column total. The row total times the column total divided by n, which is the overall total. Okay? And so the null hypothesis always is there a relationship between, no, not is there. There's no relationship between these two variables. The alternative hypothesis is that there is a relationship between those two variables. Okay, so let's look. This is actually pretty easy to do in Excel as well. I'll just model that. So I'm going to copy everything over. And then I've got Excel, I've got another sheet. I'm going to paste it all, but I'm going to remember to paste it like this. Okay, so these are the totals. Now, sometimes you may not even have the totals. These are actually pretty easy to do in Excel as well, right? Like, let's say we didn't have the totals. Delete. Didn't have the totals, we could just do sum of these two, and whoops, and enter. We get the same numbers. So that's the totals. This is the sum of what? The 355. It's the sum of these two or these two. It doesn't really matter. You get the same number. So it's just the total number of observations. So the way you read this is 21 is the total number of people that got better score on their math, that pictured themselves as Academy Award winners. Okay? This is the total number of people that got a higher score on verbal that pictured themselves as Academy Award winners. It's kind of interesting that more people that got a higher score on math that thought of themselves as great actors someday. Nobel, 79 verbal, 68 seems like almost the reverse. Olympic, more people on math. Anyway. Okay, so how do we get expected counts? Let's look back down here. Expected counts is the row total times the column total divided by n. So we could say equals, this is the row total times the column total, and that actually doesn't really matter what order you get that in. Okay. Divided by this n. It's a little bit, I don't know of a fast way to just fill it all in, because they're they're going all over the place. So it's this one times this one divided by this guy, and so on. So I'm just building out the same exact table. Equals this one divided by this one divided by this one. That's what I'm doing. Oh, sorry, it's times. Okay, so those are the expected counts. Equals this times this divided by that equals this times. And then just the last two. So now I have all my expected counts. See my expected counts, do they match what I calculated before? Yep, they do. So I got it right again. Okay. So that is this is the actual, and this is the expected. Actual, expected, actual, expected. Okay. All right, now, it is probably good to do this at least once. I can still get the observed minus the expected times the expected. But now I have to do it 6 times, not just 3 times, because I have 2 categories and 3 categories. All right, so let's do this at least once, like I said. I don't actually have the numbers on here. But, so this one is going to equal the observed minus the expected. I'm going to fill all that out. and fill it down. So those are just the observed minus the expected. Then I could say that's going to be the observed squared. Fill all those down. And then I need to do that where I say the observed divided by the expected. Now, the expected values are back up. The total divided by the expected. So these are my contributions to chi-square. I have 6 of them. Which way do I total them? It doesn't really matter. The sum of all of these is your chi-square statistic. Every single one of them. So you just get the sum equals the sum of all of these numbers. And that's your chi-square statistic. 13.2261. That actually is on the table, especially if we consider what the degrees of freedom are. The degrees of freedom is a little different for a contingency table. It's the number of degrees of freedom in the rows times the number of degrees of freedom in the columns. But the way you calculate the degrees of freedom in the rows and the columns is subtract 1. So it's basically 1 times 2. Oh, looks like I'm just barely off of the table, actually. And so that means that my number is smaller than 0.005. Let me show you that you can also just do the chi-square test like we did before. So it doesn't really matter if you have your expected values don't have to be a single column. They can be rows and columns. So I can choose this range and then choose this range. So I can choose these guys as my actual range. And remember, this was my model, my expected range. And I get a value of 0.001101. So it's really small. But it's actually not like tiny, but it's definitely small enough to reject the null hypothesis. So remember, what was the null hypothesis? In all cases with these contingency tables, the null hypothesis is the same. Not that they're the same. Remember, we're looking at 2 different categorical variables. Yes. So the null hypothesis is actually that they're not associated. Right? What's that?
Yeah, no, I had that written down.
Yeah. The null hypothesis is that they're not associated. So we reject that and we say that there is some association between that. Now, the association in this case, I think, is probably the opposite of what we would have expected, but there's still some association between those 2 variables. So it's up to us to interpret those results, but that's what we would do. So that is the that's the message I was trying to get across. Okay? We still have to do some interpretation here. The chi-square test for 2 categorical variables only indicates that the variables are associated. You can look at the contribution in each cell for the possible nature of that relationship. So that's the contribution is these numbers right here. And so if your observed and your expected are about what they should be, your contribution will be lower. So here in the Nobel are the higher values. And these are still pretty long over there in the Olympic one. So those are the ones that are significantly, or not significant. I guess I shouldn't use the word significant, but those are the ones that make a bigger contribution to the relationship there.
So the goodness of fit test is the null hypothesis there is that there's no difference between expected and actual.
Right. The null hypothesis is that the expected matches the actual, or a better way to say it is that is that the observed distribution came from, I'm sorry, the observed counts came from that distribution, that expected distribution. And so with that goodness of fit test, you can put whatever observed proportion you want in there. You make up the observed proportion. I mean, you could say it should be uniform. You could say it should be Poisson distribution. You could say it should be. You could say it should be whatever. We did 2 examples of it. Whatever. You know, it should be related to the actual births or something like that. Okay. But with the contingency tables, you're just testing for association. So your observed. Your expected should always be calculated using this formula that we come up with, where you take the row and the column. Totals, this formula here. You take the row times the column divided by the total. It should always come from that to get your expected values, because you're just testing for association. Your book exclusively calls this test a contingency table analysis, but we're using the exact same numbers. So the formula 12.5 is that row times column divided by n. Right? It's the same formula. Your chi-square contingency analysis is the same formula that I have on here, except for it has the proper notation for the totals. You're basically just totaling everything. All right. All right. So here's an example taken from the world of the environment. Okay. So here we're trying to determine if metal tags actually harm penguins. So we're looking over a 10-year period. We had a bunch of penguins that were tagged using metal tags, and a bunch of penguins that were tagged using electronic tags. So 20% of the metal tag penguins survived, 36% of the 189 electronic tag penguins survived. So is there an association between the type of tag and the survival? That's what we're going to test. So the type of tag and survival are not associated. That's the initial hypothesis. Now the thing about this is, what if we had 3 different types of tags? We could still do this test. Or we can't have 3 different types of survival, right? Everything is dead or alive. I mean, maybe, but if we did have a different type of survival, like they were walking around, I don't know, barely there or something to measure that. So here's our 2 categories, survived and died. Interestingly, we could, because everything falls into 2 categories in both cases, we could not do this as a contingency analysis and do this as a chi-square analysis by just throwing out one of these 2 categories, died or survived, because everything falls into one or the other, and then just looked at metal versus electronic, the proportion, looking at the proportions of the. Anyway, I'll explain that in a second. Let's just talk about this as a contingency table analysis. So we've got our contingency table analysis. Okay, so we said that 20% of the 167 metal tag penguins survived. So we could fill out our table like this. Okay, so we've got the number that survived versus the number that died. And then we've calculated the proportions here of the expected, which the expected proportions were just taking the row column, the total column, dividing it by the total row total, the column total, and multiplying those together and dividing by the overall total to get these numbers.
Yeah, let's just let me just copy this table over. I should have put the answer in there. Oops. Actually, this will only take a second, so let's just do this one more time. Okay, so how do we get the row totals? Like this. So now I've got the two row totals. And the column totals, and if I just fill this all the way down, I'll actually get, whoops, this will be the total overall. And I can do this is equal to this times this divided by that equals this times this. Oops. What did I do wrong? I don't know how I picked the wrong one there. Equals this, I'm sorry, no, this divided by that, or times that divided by this equals this. So do my numbers match up? Yep. So now we could just do the chi-square instead of the... It's only 2. Oops. Hold on. There we go. Comma, these guys. And I get a value of 0.000705. That's my chi-square value, which that's the actual p. Sorry, that's the actual p value, not the chi-square value. So we reject the null hypothesis and state that there is a relationship between metal tags and the penguin deaths. All right. That's a 2x2 table. Because each of these variables, this is what I was trying to explain before. Because each of these variables only have 2 categories, we could have done this as a difference in proportions test. So remember back when we did difference in proportions test, we actually would have gotten the exact same p-value. For 2 categorical variables with 2 categories each, you can either do a difference in proportions or a chi-square test. Either one works. If you have more than one category, if you have more than 3 items in any, it's the same test basically. What we learned about today. If I should have. I didn't cover the KS, the homework. Just doing that software to basically test because it frequent. It's all tests compares them to a. It compares them to either a standard normal curve or another curve, a cumulative distribution. All right. I plan to do one more demonstration here, so we can go ahead and do that. I have a lot of time left. Okay. So I'm going to minimize. I want kind of like a practical demonstration of data it through as an ArcGIS. Uploaded one called county. Necessarily, you can follow along, or you can just observe. But I'm going to use some real data and do an analysis that way. So I got my counties.gdb. I'm going to save that. I'll just put it in C10. Save that. So this isn't any special data. It's just a county GIS data. So the first thing that we want to do. Oh yeah. Hold on. First thing we want to do is reauthorize ArcGIS on this computer, which is already authorized on your computer, so just bear with me for a second. Provisioning. This literally only take like 2 or 3 minutes at the most. Every year this has to be done. If your license on your computers is expired, just let me know. It does require the internet. All right. Awesome. We're all set. So what we're going to demonstrate is just a few tools. Has anybody here used a pivot table in Excel before? Okay, so we're going to demonstrate taking this ArcGIS data and calculating, getting it ready so that it's in categories, and then changing those categories into counts. Because that's actually, even if you went out and did a survey, you're probably going to have a row for each respondent of your survey, right? And then you have a column, and you could have some categorical columns. Like you could say, male, female, or you could say income group, high, medium, and low. So you could have those in columns. That doesn't look like the data we just got ready for chi-square, does it? It's in counts. So there's a quick way to do it in Excel called a pivot table. So that's what we're gonna demonstrate here real quick. All right, so I'm gonna add my counties data, which I put in CTEMP, counties, and there's a bunch of values here. So we just have to pick one. So we have this one called average family size. So in other words, how big is a family living in a unit? Now that's not a categorical variable right now, right? That's a number. It's talking about an average. So it's a mean. However, I can summarize a column. Not summarize, I meant the statistics. Okay, and you can see it's kind of neat that that's actually pretty normally distributed. Okay, I get I get frequency distribution there, and there's a little peak. It looks like there's a little, of course there's a little tail this way, because you can have a minimum number of kids, but you can't have a maximum number of kids. Right? So, I mean, I guess theoretically there is a maximum number of kids. I had 4, which is, a fair bit. Okay, so what if I wanted to break those into categories? So we got this average family size, we hit apply, and you can see that we've got this map here. You can see that there are some larger families in the interior counties in the west, and all throughout here we've got some larger families in the south. The north pretty much has less counties, less size in general, lower family size. But let's just change this into 3 categories. Maybe natural breaks will work. So we can just call those small, medium, and large average family sizes. And the breaks are 2.96, 3.27, and 2.74. So I'm just going to write those down. You don't need to write those down, but I'm going to write them down just so that I have them. 296, 327, and 472, 471. 47? What doesn't really matter. We can write 5. In fact, so what I want to do is come up with a new categorical variable. So I add a field. Can't add a field. I can't add a field. I'm going to have to convert this to a shapefile anyway. So I'm going to do that right now. Maybe that'll let me convert it to... Okay, so now I'm going to add a new field, still blanked out. Oh, oops. Why is add field? Anybody have an idea why that is? What am I missing here? Doesn't say read only. Interesting. All right. I wonder what would happen if I did it through our toolbox.
Did you put it in that GeoDatabase?
I didn't put the new one in the GeoDatabase, and this is the new one. This is just a shapefile.
For me, it just exported as a shapefile. The first time
Oh.
I did it, I put it in the GeoDatabase, but the second time I did it.
Well, the second time I tried, but I added the wrong one. Counties.shape. I added the wrong data set. I added the one that was in the GeoDatabase. That's right. Yep. Okay, so we're just going to change. It really doesn't matter. Like you can do, as long as it's really categorical. You can do high, medium, and low as 1, 2, and 3, or
or you can actually write the words high, medium, and low. So let's actually write high, medium, and low in this case. So we're going to call this family. Now that it's a shapefile, it won't fit too much. I'll just do family as Z. Okay? And so I find it easiest to change everything to one of the categories, such as low, quote, low, quote. So now I have a column, and everything's been changed to low. Why didn't that work? Oh, I didn't choose the right field? No, I did. Did I make it a... I'm going too fast. I made it a string. Okay, double quote, sorry. Low, and then I can select by attributes and select only those that are where family size, average family size is greater than 2.96 and average family size is less than 3.25. 27. Okay. Hit apply. Now I can change all of those to medium. And then I can change this just to say average family size is greater than 3.27, and I get all the rest of them as large. It doesn't really matter if you spelled large different, as long as they're all the same or spelled medium different. So see I have them all as low, medium, large, low, medium, high. Okay. So we got those categorical variables. And then I could, actually, I think what I'm going to do is selection, clear selected features, and I'm going to calculate the population density add field. I'm going to call it popden and make it a float. And then I'm going to calculate the population in 2010 divided by area, shape area. So now I've got population density and family size. I'm going to see if there's a relationship between population density and family size. So that's my category. I still have to do one thing though. I have to change population density into a categorical variable. So I'm going to hit statistics one more time. It looks like this distribution is highly skewed. I think what I'll do is, just to make this real simple, I'll add a field. I'm going to call the field pop. I'm just going to call it pop stat. I'm going to make it text. And what I'm going to do is just sort by population density and choose roughly half the counties. How many counties did I choose? Yeah, 1,451. That was almost half the counties. So I'll say field calculator. So these are the higher population counties.
And then I'll switch the selection. Under selection, you can say, no, here it is. This button, nope, this button, nope, this button. Switch the selection and field calculator low. So now I have two different categories for counties. My pop stat has the high versus the low density counties. Okay, the lowest density county here being in Alaska somewhere. I probably should actually delete Alaska because it's got these really large counties that are obviously going to have pretty low population densities. But I'll just leave them in for now. Actually, you know what? It's not going to be that hard to, I'm going to select like that and then say export one more time. I'm going to call this lower 48. So I did get rid of Alaska. I'm not going to add that to the map. So now I'm going to open the DBF up in Excel. The DBF, the reason why I exported it to Excel is so that, as a DBF is so that I can open it in Excel. So that's in C, temp. I call it lower 48. I need to open up I'm just going to say all files. I need to find lower 48.dbf. So I need to get the .dbf file. The dbf file will open in Excel. I'm going to hit open. It's going to be a lot of information. There's still about 3,000 rows. So what I need to do is I want to get rid of all of the other rows that are there. I'm just going to go and delete everything besides family size and population stat. So now, I'm just doing that for organizational purposes. If you don't want to do that, you don't have to do that. But now I've got family size and pop stat. So now it's in a state where it's almost ready to start the analysis. So I have my two categorical variables here. These could represent lots of other map data sets. You could have a land cover data set, and you could be looking at land cover and some other thing. Obviously land cover is correlated to population, but you could habitat type and the population, see which habitats were the most threatened by human encroachment or something. All right, so we've got low, medium, high, pops, just low and high, right? So we need to create this thing that I called a pivot table before, right? So to create a pivot table, you can select two items. Where is it again? Is it under data analysis? Is that one of the data analysis tools? Hold on a second. I thought it was a right click. Let me just. And hopefully, maybe, I don't know if this works in Mac or not, but it should. I just want to know where it is. Insert tables, pivot table. Insert, pivot table. There we go. So it's under insert. Insert, pivot table. So we hit pivot table, and if you already have it selected, it'll show up. So if you don't, you can select this little up arrow and actually select the pivot table, the columns that you want. Like I want D and E. I'm going to put it in a whole new worksheet because I think that's easier. So I'm going to hit OK, and then it's going to show up here. Choose fields to add to the pivot table. I want to add both family size and population statistic. This is a different interface. Family size. And that's exactly. You want to get that number of items. And delete these other sheets. All right. Yeah. I thought that maybe I'll have to make a video on this later. Some values. This is a little bit different interface than the last one. Large, low. So this is the way it should work. Large, low, medium, and we should have we should be getting the totals there. I wonder. I mean, we shouldn't. I don't think we should have to do this, but I think this might work. So I made a column with counts. I'm just going to pull down here. Yeah. Hold on. There's got to be a way to make everything equal, but what I can do now is I can do that insert pivot table just to show you, see if this works. Okay, so we got family size, population, we move one of these into the columns, and the count, yeah, there we go.
I don't know why I had to create that dummy column. I haven't had to do that before. Now these numbers aren't right. I have to fill down the rest of this column for those to be right. So I created this dummy column with a bunch of ones in it. So it's counting that, it's literally counting that number 1 every time. So every time there's like a medium, it counts that number 1 and throws it into the column there. Okay. So it probably would have been easier to create this dummy 1 column in ArcGIS if I knew I had to create it. So I've got all those ones. Now this number should be correct. Did those update? Just to make sure that they updated, I'm gonna delete it one more time just to demonstrate how to do it. So what you do is you highlight the 3 columns, one with the dummy 1 data, insert pivot table, say okay. One has to, you can add all 3 of them to the table. One of these 2, let's do family size in the columns, has to be in the columns, and the count has to be in the sum value. So now we have, 53 were high density counties that had large families. 72 were low density counties that had large counties. So we have a lot more in this second category, low, and low high. But we want to find out if there's a relationship between the population density and family size. What we have to do is to create a contingency table. Well, sorry, not a contingency table. We have to create the expected values. So the expected values is simply, remember, this times this divided by this. So this actually creates a contingency table for us. So we can use these exact numbers in our table. So we go, okay, and we do that for all 6 values. These are our expected counts. So if there are no association between the variables. Did I get both of them? Yeah. Divided by. If there are no association between the variables, this is the distribution we would expect, and we have the same number of counties. This is the distribution we would expect. So we're going to test to see if there's a relationship between these 2 variables, family size and density. So now we can just do the chi-square test. Here's the actual range. Here's the expected range. And there is our statistic. Now, our statistic's really, really small. So we're going to what? Accept or reject null hypothesis. Reject, exactly. What was the null hypothesis in this case? That there was or was no association? No association, exactly. There's no association. We're going to reject that, and we're going to conclude that there is an association between family size and population density for these variables. And we could, for further analysis, we could actually calculate those intermediate numbers to see which ones had the biggest contribution. My guess is that these large counties, that category looks pretty close to the same. So that's not going to be a big contribution to the chi-square. But these numbers, both of these numbers look I mean, they're totally flipped, and even not flipped, but that's still one. But these two are flipped in terms of what you would expect. So
It's the low and medium that aren't as expected. All right, so that's one example using ArcGIS and Excel using a pivot table. I've used pivot tables a lot before, and so I didn't practice right before class. You know, it's like when you make a thing, you're like, oh, I've done this before so many times, I forgot how to do it. Because I haven't done it in a little while. So anyway, but I do this like in the 315 class. I make a pivot table for doing just what I said, looking at the difference between two maps and seeing if the contingency table says that there's a difference between those two categories, bigger categories. All right. I don't have anything else for today other than let's look at the homework really quick, and then I'll be quiet. So for today's homework, I did say modules. Just skip the KS analysis. So I'll show you right there. So under Chapter 12. I said skip the KS questions. I'll open those up just to make sure everybody knows what I'm talking about here. Okay, that's these guys right here. Test for normality. So question 4 is the one you skip. Okay? And then you're going to actually here's a contingency table for land cover change, like I was talking about. We do this very similar exercise in GHY 315 for the undergraduates. But here is 1970 versus 2000, and so we're doing a contingency analysis here to see if the categories are associated with each other, or if there's a lot of changes over the land. So you're going to do the same thing. This is pretty easy math this week. So you can put it in Excel, or you can just type it all in. But it's just this number times this number divided by that number, this number. You have to do that. In this case, how many times are you going to have to do it? You have to do it 9 times. It's a little bit different than any examples we did, but not much different. You just have 9 different values to come up with expected counts. Does that make sense? All right. And then you've got a soil classification. It's the same deal. These are your totals. Kind of the weakness of the homework is that it didn't talk about how these data sets were created. That's what I was trying to demonstrate with the ArcGIS data. One way to do these is to create a pivot table from GIS data. So these soil samples could have been points that you extracted from a map. So you had each soil sample had whether or not it was well, moderately, or poorly drained, whether or not it was an entisol or an aphisol or I'm not a soil scientist, so I'm not going to try to say that last one. Okay. These are also pretty straightforward. This is really this is really similar. This is looking at just one category. This is kind of an interesting way. Remember I said you could look at, I think my exact words were, you could look at race and distance to certain services. Well, this is looking at distance to K, but we're not using the raw distances. We're categorizing the distances and looking to see if there are a certain number of, in this case, looks like visitors away from a religious organization. So it's a service, but it's an example of that. Okay. All right. So we'll just end there, like 20 minutes early. That's fine. As I said, I'm going to be gone, so if you have a question, don't wait for me to appear in the hallway on Monday or Tuesday or Wednesday, because I won't be here. I get back, my plane lands at like 4 p.m. on Wednesday, and I'll probably just go home. So send me an email if you have a question. One thing I'll do, though, because I'm going to be gone, is I'll change the due date for this one till the next Tuesday. So I made it April 4th, and I'll make it April 10th. But I actually think there's a little bit of a there's not. I don't think this is a super difficult, especially since we threw out the KS test. This is not a hard homework assignment. Probably get it done pretty quick anyway. All right, so I'm going to stop the recording. If anybody has a question they want on the recording,